So in this video, we're going to be solving the 2015 AMC 10A problem 14, and it's about angles. So I haven't really uploaded many videos of geometry, so yeah, I'll just try to work on that. So the problem says the diagram below shows the circular face of a clock with radius 20 cm and the circular disc with radius 10 cm externally tangent to the clock face at 12 o'clock. The disc has an arrow painted on it, initially pointing in the upward vertical direction, and we're going to let the disc roll clockwise around the clock face. At what point on the clock face will the disc be tangent when the arrow is next pointing in the upward vertical direction? So if you think about it, if you think about the scenario, then it's actually pretty complicated, and it can't be really solved by intuition. So what we can do is we're gonna split. So what we want to do is we know that the overall angle that this turns is 360 degrees because it goes back into pointing upward. So it would have turned 360 degrees overall, but we don't know how to observe that angle intuitively. So we're going to split that angle into components, and to angle components that we can easily think about. So I'll show you. So let's say theta. I'll redraw that. So let's say theta is the overall angle, and we're going to call theta C. We're going to call theta C the angle that, let's say it goes to T o'clock. If it goes to T o'clock, if let's say this goes to T o'clock, then and it turns around the clock by an angle of theta C. Okay, I'll get rid of that T. Yeah. So let's say it moves somewhere here and it turns by an angle of theta C. So it went around the clock by theta C. So yeah, we're gonna call that angle, like the angle that it goes around the clock by theta C. And then actually I'm not gonna spoil it for you yet. And then let's call theta R. So the angle that this turns relative to the surface of the clock, or relative to the center of the circle. So what I mean is, if we consider this surface, the surface of this clock as not the circumference of a circle, but a flat surface like this, with 12 o'clock, 1, 2, 3, and so on. And then we have our arrow starting here. That's a really bad arrow. That's a really bad circle. And it's gonna turn. It's gonna rotate along. So basically, what I mean by like relative to the surface of the circle, of the clock, is considering it as a flat surface and then looking at what angle this will turn by if we consider it like this. And we're gonna call that angle, yes, theta R. And I just did R for this because relative, and C because around the clock. But also, yeah, we'll just try our best not to get confused. So yeah, and we can easily easily see that these two angles added together. So if theta R is the angle this rotates if the surface is flat, and then theta C is the angle that it turns around the clock, then then intuitively it's like the overall angle it has turned would be the angle that has turned relative to the clock plus the angle it has went around the clock to get the overall angle. Because yeah, so we add this to account for the circular surface instead of the flat surface. So we can see that theta is equal to theta C plus theta R. So yeah, so some people who are familiar with competition math would find that theta C is actually pretty easy to get. Well, I'll show you later. But theta R, well, I'll show you later. So basically, the reason we're doing this is, so as I explained before, we're splitting it into easier components to visualize. And what we're trying to do here is, we know this is going to be 360 degrees. We want to find the T the position that this will be, so the t value that is going to be at, so that if it goes to t o'clock, for this to be 360 degrees. And we're going to put these two terms in terms of t so that we can solve for t, as this is equal to 360 degrees. So yeah, that's all we're going to do. And I'm going to erase this as it takes up too much space. Yeah. Okay. So now we're going to make more observations. So we're going to try to put these two in terms of t. But before we notice that, so firstly, we see that they gave us the radii of the two, of the disk and the clock. So we'll have to use that in some way, unless it's a trick for the question by the question maker. So what we can see that is, let's consider this a flat surface again, but we're gonna kind of condense it a bit. Oops. Wait a sec. Okay, so let's say it goes halfway. Actually, I'm gonna call that 0 so that we don't get confused. So let's say this is half of the circumference of the circle. Then we know that I need to put this in different colors. Let's say that, so that will be, so the clock is radius 20 cm, so the circumference would be 2 times 20 times pi, which is 40, and 2 times 20 times pi, which is 40 pi. So half the circumference would be 20 pi. And then if we draw our disk, that was pretty good. The circumference of this is equal to 2 times 10 times pi, which is 20 pi. So we know that if a circle moves rolls across a distance equal to its circumference, then it's pretty easy to visualize. It's kind of like kind of stretching out this circumference along as a straight line across this, and it'll exactly equal this, as the circumference is exactly equal to the distance. So when it travels exactly this distance, then it's going to be back here facing, oops, yeah, I'll leave it green, facing upwards. Yeah, so it's going to be, so theta r is going to be 360 degrees. Theta r is going to go one full direction. Go like rotate fully, so 360 degrees. But then theta c is just half. It's just 180. So it only rotated halfway around the circle, while theta r went full around, because yeah. So that means theta r rotates. That means theta, for every degree this rotates around the circle, is gonna rotate twice as much relative to the circle, because because when it goes halfway around the circle, it goes full rotation relative to the clock. So that means, if we put it in terms of what we did here, actually I'll put them in different colors so that you guys don't get confused. So that's theta r, theta c. Alright, so to remind you guys again, this is, so to remind you guys again, this is theta c, so the angle around the clock. And then theta r is relative to the clock. So we found that, so this goes twice as much, and for every degree of around the clock, it goes twice as much around the clock, so relative to the clock. So we can deduce that theta r is equal to 2 times theta c. Oops. 2 times theta c. So for every degree we go around the clock, we go twice as much for relative to the clock. So yeah, okay, that was a bit that could have been a bit confusing, but if you stop and think about it for a while, it will start to make sense a bit. So yeah, so we can substitute this into here to just get theta is just equal to 2 theta c plus theta c, which is just 3 theta c. There we go. But then, so we just have to find theta c in terms of t, if this goes, yeah. So that's pretty easy to see because, okay, I need a bit more color. So if we see, so whole rotation, so let's say it goes to t o'clock. And we know that a full rotation is 360 degrees. So if it goes around the circle by, if it goes around the circle to reach t, and we want to find the angle theta c. It's basically the proportion of the clock covered times 360 degrees, because 360 degrees is like, basically it means like covering the whole circle. So the proportion of the circle covered by, when it comes to t, it will be t divided by 12, because there's 12 slots, and then t is like the teeth slot. So we can just write it like theta c is equal to the proportion, which is t over 12, times 360 degrees. Yeah, so that's pretty intuitive. Yeah, it would be good to kind of be good at thinking like this, because these kind of clock problems with angles, like it really often uses this kind of formula. So yeah, so we've found this, so we can just plug this into here to solve for t straight away. So just to summarize though, so and also we can clearly see that we can see that t is, the answer choice is always say something o'clock, so we can assume that t is some integer. Yeah, so theta is equal to, we plug it in, 3 times t over 12 times 360 degrees, which is equal to 3 times, so 360 divided by 12 is 30, so t times 30, which is equal to 90t. And we want to find t so that theta is equal to theta is equal to 360 degrees, because we want it to be next pointing back in the upward direction, so when it turns 360 degrees overall. So we want to find t when theta is equal to 360 degrees. So 90t equals 360. Oh, forgot to put the degrees. Then t is therefore equal to 40. Oh, no, t is equal to 4. So t is equal to 4. Therefore, this would have turned 360 degrees when it is at 4 o'clock. Yes, so the answer would be this. So yeah, so it's kind of interesting to see, because we can see that the clock is exactly twice the circumference or radius or of this radius or circumference. So it feels like it's gonna be somewhere like at the it just feels like it's gonna be at it's gonna turn exactly 360 degrees, like here or somewhere halfway, or like a quarter or something that seems a bit more legitimate to like our kind of innocent intuition. But we have to always be aware of the what challenges this intuition, like what kind of facts are we skipping to make that judgment. So here we split it into components, and easier components. Well, this wasn't that easy, but then we put this in terms of this, which made it easier to see, which made the equation much easier, and we could easily find this in terms of t, and then we could easily find the t-value for which this is equal to 360 degrees. So yeah, so the main takeaway from this video would be that angles, always try to divide it into components when you can, so easier components, because really it's not that easy to visualize visualize the over angle, so visualize theta in this case. So yeah, so thanks for watching this video, and hope to see you in more of my other videos.